Hello, welcome to Numeristical. We're continuing our deep dive into AUC. We are now in part 3, which is showing the equivalence to pairwise comparisons. If you haven't yet checked out parts 1 and 2, I recommend you look at those before watching this video. I'll put links in the description and also up here on the screen. So today we're going to demonstrate an equivalence to pairwise comparisons. Now in the previous video, we walked through how to actually draw the ROC curve, and we learned a bunch of details, and we walked through an example. But one of the things we struggled with was that while we understood that if you had perfect prediction, that is, all the ones were at the top of your ranked list and all the zeros were at the bottom of your ranked list, then you would have an AUC value of 1. And if there was really no relationship, you would have an AUC value of 0.5. But we didn't really know how to put into context numbers in between 0.5 and 1. Clearly, it's better to be closer to 1, but we wanted to give something a little more tangible as to what these numbers in between 0.5 and 1 really mean. So we're going to demonstrate that today, and it's going to show a really nice correspondence between playing a game of pairwise comparisons and the actual drawing of the ROC curve. So to start out talking about this, let's play a game with our model. So if you remember, we had a model where we were considering a fraud detection example, and it gave some scores to transactions as to whether we thought they were fraudulent or not, and a higher score meant that it was more likely that this transaction was fraudulent. And we show that actually all that matters is the ranking of the relative cases and which ones were ones and which ones were zeros. That was all you needed to compute the AUC score. So now we're going to take that same test set. Imagine we have a test set. We have this ranked list of cases, and some of them are ones and some of them are zeros, and we have them ordered in what the model thinks is more likely to be fraud. And we're going to play a game. We're going to randomly choose a 1 from the test set. So by 1, I mean a positive case. So in the case of the fraud detection, this would mean we choose an example of fraud from our test set. And we also choose a random legitimate transaction from the test set. And then we ask our model to score and rank those two cases. And we ask the question, is the model right? And we're trying to get what's the probability that the model is right under the circumstance when we chose the 1 and the 0 randomly from the test set. And what we mean by the model being right is that it ranked the 1, the true fraud case, as being more likely to be fraud than the 0, than the legitimate transaction. So we can analyze this. So this is the same set of scores and cases we considered before. So on the left are the scores our models assigned, and on the right is a 1 for the cases that the model for the cases that were actually fraud, and a 0 for the cases that were actually legitimate transactions. So to give an example of this game, let's walk through the following thought experiment. So we choose a random 1. Suppose we choose this one colored in blue. And then we choose a random 0. Suppose we choose this one down here colored in green. And in this case, the model is right because the 1 was deemed more likely to be fraud than the 0 by the model. But you could imagine another scenario where we choose this 1 and randomly choose this 0. Now in this case, the model would be wrong because the case that was 0 actually was deemed by the model to be more likely to be fraud than the case that was actually fraud. So this is an example where the model is 0. So the idea is we're going to play this game, lots of times and say what's the probability that the model is right under these circumstances. So to make this a little more, make the notation a little cleaner, I'm going to define an event called R, and I'm going to say R is 1 if the model is right and 0 otherwise. And so what we really want to get at now is what is the probability that R equals 1? If we played this game, what would be the probability that our model would be right in a particular instance of this game? So we can use the law of total probability to break out this probability. We're going to compute this exactly for this test set. And the way we're going to break it down is we're going to say, well, there's 5 1s, and each of those 1s is equally likely to be chosen as the 1 in this game. And then we're going to randomly choose a 0, and given each one, we can say what's the probability of us being right given the particular 1. So let's walk through each of these in turn. So let's say the first one is chosen. That means the one at the top of the list, colored here. Well, if we choose this one, we know for sure all of the zeros, whatever zero we chose, the model is going to be right in this case because it ranks that one higher than all the zeros. So given that the first one is chosen, the probability of the model being right is just 1. It's 10 out of 10. All of the zeros, all 10 of the zeros ranked lower than this particular one. Now, when we go to the second one, we have the same exact deal. This one is ranked higher than all of the zeros. And so, again, we can be assured that if that one is chosen, we will be right. Now, if we choose the third one, we're pretty likely, but there's 1 zero that ranks higher than that one. So in 9 out of the 10 cases, the model will be right if we happen to choose the third one as our 1 for this example. So in that case, we'll have a probability of 0.9. Likewise, if we choose the fourth one, now we do a little worse. Now 7 out of the 10 zeros are lower than that one, but 3 are actually ranked higher. So if we chose the fourth one, we'd only be right with probability 0.7. And if we choose the last one, we would only be right with probability 0.4. That's the worst case in this example. And so putting it all together and saying that each of the ones has probability 1/5 or 0.2 of being chosen, we get that the probability, adding up all these numbers, is 0.8. And if you remember from our previous example, when we computed the AUC by hand by drawing out the ROC curve, we also got a value of 0.8, and this was not a coincidence. So the AUC is always exactly equal to the probability of the model being right when you play this game. And you might even notice a further correspondence. You might even notice that these 5 terms, the 0.2 was the height of each of the rectangles that we drew in the last lecture. And the corresponding numbers are the widths of the 5 rectangles that we chose. So these 5 intermediate terms are actually the areas of the 5 rectangles that we drew. And we're going to show why this is true and how this nicely lines up. So now we're going to show a relationship between the ROC curve that we drew last time and this game that we're playing with these 1-0 pairs and seeing if they're correctly ranked. So we're going to take the same answer list we just had and the axes for the ROC curve that we had before. And if you remember last time as we drew the ROC curve, we noticed a few things. One was that we always moved up 1 step or to the right 1 step. We moved up in increments of 0.2 because there were 5 ones, so we always moved up in increments of 1/5. And we always moved to the right in increments of 1/10 because there were 10 zeros. And every time our threshold went below a 1, we moved up 1 step. And every time the threshold passed by a 0, we moved to the right 1 step. And we're going to see how this is now naturally related to the pairs, these 1-0 pairs. And the first way we're going to show this relationship is that each row corresponds to a particular 1. So the bottommost row out of 5 rows is going to correspond to the first one. The next row corresponds to the second one. The next row corresponds to the third one, then the fourth one, then the fifth one. So we're counting the ones from top to bottom, but we're counting the rows from bottom to top. And similarly, each 0 corresponds to a column. The first 0 on the list, the highest ranked 0, corresponds to the leftmost column, and then the next 0 corresponds to the next column, and so forth, until we get to the rightmost column, which corresponds to a 0. So looked at it in this way, we can also see that if we have a particular 1-0 pair, and we look at where the row for the 1 intersects the column for that 0, we get one of these unit rectangles. So we're going to have a unit rectangle that corresponds to each 1-0 pair. And what we're actually going to see is that this particular rectangle will be under the curve if and only if that 1-0 pair is correctly ranked. And that's going to give us a nice correspondence between the area under the curve and the probability that the model makes the right decision when you pick a random pair. So you could see this 1-0 pair corresponds to the 4th row, counting from the bottom, and the 5th column, counting from the left. this particular unit rectangle corresponds to counting the fifth one, counting from the bottom, so the lowest ranked one, and the second highest ranked 0. And similarly, this unit rectangle corresponds to the 1 and 0 I've highlighted on the right. Okay, so let's revisit now drawing our AUC curve, and let's really think about what we're doing when we take each step. So again, when we take the first step and we pass by this 1, what are we saying? Well, we're saying that this 1 outranks all of the zeros because it's the very first thing we see. And so when we draw the curve, we go up 1 step. And what we now can assert is that this entire rectangle is going to be under the curve. Because again, we're only taking steps up and to the right, so we can never go back down to sort of cut into any of that area. So once we take that step up, we know that that entire rectangle is going to be under the curve. And that makes sense because all of those 1-0 pairs that involve that 1 are correctly ranked. If we choose that 1, we will always get the right answer because this 1 outranks all of those zeros. Likewise, we pass another 1 and we get the same story that this 1 outranks all of the zeros. So we add another full rectangle that we can guarantee is going to be under the curve. Now next we get a 0. So what does this mean? Well, having this 0 means that this 0 outranks all of the remaining 1s. And so what that means is that everything above this is guaranteed to be above the curve. So we know that we missed all of these. And this is corresponding to the fact that this 0 outranked 3 1s. So that's 3 unit rectangles that we're going to get wrong. So that corresponds to area that's going to be above the curve rather than below the curve. Next, we get another 1. And again, now we say, okay, this 1 outranks all of the remaining zeros. Not that 0 that we just passed, but the remaining 9 zeros, this 1 ranks higher than. So we get another rectangle with width 0.9 that's guaranteed to be under the curve. Next, we hit another 0. We know that this 0 is going to rank higher than the 2 remaining 1s. So we can assert that those 2 unit rectangles above this little segment are going to be above the curve. We get another 0 that gives us the same thing. Now we get another 1. Well, we know this 1 is going to outrank the remaining 7 zeros, but not the 3 zeros that we already passed. So again, we add another rectangle like this. Now we get 3 more zeros, and we add in 3 more little red rectangles that say that those 3 are cases where the 0 outranked the 1, and the model did a poor job. And then finally, we hit the last 1, and that brings us to the top, and we're guaranteed that all of the remaining area is now going to be under the curve as we finish drawing out this curve. So let's review what happened here. So our test set contained 5 1s and 10 zeros. And so there are 50 1-0 pairs. 5 ways to choose the 1, 10 ways to choose the 0. And similarly, there are 50 unit rectangles because we said there's 5 steps of 0.2 to go up and 10 steps of 0.1 to go across. And there's a natural correspondence. Each of these 1-0 pairs corresponds to a unit rectangle. And we know that the unit rectangle is under the curve if and only if the model ranked that particular pair correctly. And so we can then conclude, well, the area under the curve tells us what fraction of the 1-0 pairs are correctly ordered. And that's the same as saying, if we randomly picked a 1-0 pair, what's the probability it would be correctly ordered? What's the probability if we picked a particular unit rectangle that it would be under the curve versus above the curve? So I think that's a really neat correspondence, and I think it's really interesting to think through that and realize that this lines up so nicely. So anyway, I hope you've enjoyed this video. I hope you feel like you've learned a lot and seen something new. Next video, we're going to talk about how AUC can be misused. This will be a more general talk about practical situations where you can kind of mangle the AUC a little bit or make interpretations that aren't really justified. So we'll talk a little bit about that, and I hope that'll be interesting to you and you'll join me for that. In the meantime, please like this video and subscribe to the channel if you haven't already. It's really helpful to me to get the number of subscribers as high as possible so that I can continue making content. And thanks for watching, and have a great day.